So hello everyone, especially those that are attending online. I advertised yesterday that we were going to focus on fusion welding today because it's important. It's a way to make assemblies and save money. And there are some pitfalls. So I brought a piece, I got a lot of examples, and we're mostly focused today on things to not worry about, but to consider when you have to assemble something and you're going to be involving welding. And that should be all done today. So the plan is next week, we only have lecture on Wednesday. And what I'll do then is I'll go over other processes. We're going to talk about powder metallurgy, a little bit about laser sintering, and kind of things that, because of the background and everything that we've talked about so far in my module, you'll just be able to appreciate and understand quickly. They are sort of cutting edge, fancy processes, but there is very little that's completely new about them. It's all about melting steel or metals and then making parts. So this is what we went over yesterday, that when you do fusion welding, you bring electrical energy, it melts the base material and also your consumable. Now, if we could spend a lot more time on welding, there are ways you weld where the electrode here, let's say it's a tungsten electrode and it doesn't consume itself. So we call it autogeneous welding, where you essentially are blending the two pieces you have without adding a filler metal, but you still need to protect against the oxidation. So that was something we emphasized yesterday, to shield that welding pool, and traditionally it's done with the slag. You worry about getting enough penetration of this fusion in the components that you're welding. That's a common issue in manufacturing, lack of fusion. And then you have to control the total heat. And this is, I do have some examples related to how you optimize your process for different applications. So that's going to be a little bit of a focus today. This slide, I left it in. It's when we were looking at those fracture surfaces this week, we were talking about, whether it happened all at once, whether it didn't happen all at once. And this very specific fracture surface, if you see it on a weld metal or anything that's broken, it means that you really had the overload. These are ductile dimples. You see the little round area. So it's all you can expect out of the material. When it fails this way, it means that it did its job. So it was just a little bit of a side note that, in addition to looking with the naked eye at the fracture surface and seeing all those lines, you can go a lot deeper, and you have to bring it to the microscope. This is approximately 500 to let's say 2000x magnification, sometime higher depending on the material, and typically use an electron microscope, because if you try to do it on an optical microscope, it gets too blurry. You have too much of a height variation. The fracture surface is rough, so you can't see. So the ability of the electron microscope, the use of it, in this case, is not so much to go to much higher magnification as it is to have a bigger depth of field. So a range of distance to the fracture surface where you're still in focus. Okay, so the first example is electrical transmission power lines. We have a lot of those, and they're subject to wind loads all the time, and also potentially seasonal variation. You can have some ice built up on them. It actually was a big issue in Canada when I grew up, and they had two options. One was to make the towers much stronger to handle the ice, but that was going to be very expensive. So what they ended up doing is they designed all the electrical circuits so they can overload each power line in sequence to melt the ice during a storm. It just speaks to, when you're talking about very large infrastructures, a lot of times what seems easiest, make it stronger, is outweighed by the scale of the effort. So having to spend twice as much money or rehabilitate, rebuild power lines that are existing was too much of an added cost as opposed to saying, okay, I've got 10 wires, so for 5 minutes I'm going to be overeating that one line until the ice falls, and I'm going to do the next one and the next one every 10 minutes. So it's just kind of, it's there. You have power, so you can use it. Now, we're going to talk here about how they make these. It's so big that quite a bit of the assembly is done in the field. So each arm going to the side here, so those are the arms that are holding the conductor. They'll be about 20 feet long. So if you take the entire assembly with 20 feet on each side, it's too long, too high to go on a truck. So you need that arm to be assembled in the field to the post. You can do it on the ground and then lift the whole thing, or vice versa. But it's the one location in the assembly where it's not welded. Right here, there's a series of bolts. And that's what you connect, and the bolts are here to the side. So the part that I brought is a section of that bracket that has the bolt to the side, and then it has the tube that extends out on the other side. So you can see they made a very, very thick bracket. It's about 1.5 inches. And the tube, so the big hexagonal or octagonal tapered tube is only this thick, 1/4 inch. And the most efficient way to connect the two together, including because of tolerances, is welding. What you'll see on the sample, there are a couple of other features, is there's a little bit of what we call a backup bar of steel behind the wall here, and that is to facilitate getting a good root of the weld. So you weld from the outside on these. So the tube is over here, and you weld from this side. So by having a little bit of extra piece of metal behind, you're able to make that first weld a little deeper, and it's stabilized, it's protected. Because you can come with all your shielding from this side, but you'll have contamination there. So the code will give you an extra allowance for the stress level on that connection when you use those bars, and it makes sense because it is giving you better strength. Another feature is you have at least 5 welding passes. So they went once, went again, went again, went again, and on the top surface, you only see 2 of them, and one is very wide. So it was a little bit wider than what you would normally want to do for this thickness. The last thing is there's a lot of reinforcement. So this weld is a lot bigger than the material itself, and not on this particular case, but we've seen in the past that what happens then, it starts cracking right there where the base material is, because you've been shrinking and you've been introducing so much stresses. So it's pretty much an oversized weld. And it's not at that point really giving you extra strength. It's most likely reducing your strength at that size. Okay, one last thing is this was cold bent from a big plate. So you can see it here, and we made that notch because one issue they had was fatigue cracking at that bent, and we're trying to verify whether it was really cold form and the kind of stresses that they were getting. So we had a fine element analysis of this, and then to make sure the analysis was correct, we made this test where we had reference points, looking at the distance between the reference point, removing material, and getting that spring back that I've been talking about. So kind of a all-inclusive sample here.
So like when you cut this out, it springs back?
A little bit, yeah. Yep. In this case, it wasn't a huge spring back because the thickness was so big, but it was really verifying the finite element analysis, and the stress levels close to the surface were very close to the yield point near the end of the part, because you really take a plate and you say, I'm going to bend it here, and I'm going to bend it here, so you end up with this shape. Okay. So what happens is, as you bend, this portion is in compression, but as soon as you let go the closing force to form the shape, it becomes in tension. And let's say we have our bolt holes right here. What happens is, when the arm gets bent, you supplement all these what we call residual stresses with the surface tension of pulling, and that's where the crack started in this case. So there are a number of ways to avoid this. The first one is to do it hot. The other one is to reheat it to relieve the stresses after you form. The idea of using such a thick piece of steel is also questionable. We have suggested variations where you'll use stiffeners. They're a little bit the same way with the radio telescope. You add 11 components, when of course if you're using just one plate, it has to be thick. But there would be other ways to have a box that will give you strength and stiffness without having those thicknesses that are harder to weld, give you more residual stresses, harder to form, more forming residual stresses. So it's a little bit of a difficulty. It's an industry where a lot of things have been done a certain way for a long time, and we have so many tools available to know what should be done to all of a sudden make it so much more performant that sometimes you get surprised. Why are you guys not doing this? Oh, well, we'll always work. We always sold it this way. Okay. Well, it's 2016, you know. We're not in the 70s or 80s anymore. So it's unfortunate, but it happens. You can see on the top surface of the sample, it was galvanized. And the idea is you do all your assembly, and when you're done, you dip it in zinc, and I'll show how that works. In probably the last two lectures, we'll focus on corrosion protection. Okay, we'll talk about joist. We started a little bit yesterday. I mentioned about the tomato greenhouse. So we'll spend a little more time today going into the details and a little bit more of the implication of having specified the welding, but not necessarily the quality control or the quality assurance that you needed. So what happens here, you have, this is up in Maine, and it's still there, and they built the second building. So it's, when you go up, even in person, you can't see the end of the building over the tomato plant. So it's a little bit impressive for that. And what happens is, if you have a snowstorm, you have to heat up that roof to melt the snow, channel it so you don't have too much weight. If you have a lot of snow, then the system can get overloaded, and then you have a little extra weight on the roof for a period of time. In this case, the first thing that happened when there's a little excess snow is they start breaking these diagonals. So the way the joist work, so we call them top chord and lower chord. So you have two big members, and they have to be connected with diagonal to make sure that the shear force is transferred. So you get tension on the bottom, compression on the top one, and those diagonals, one of them carries tension, the other carries compression. So it's alternating this way. The very first one is a tension one, and a lot of times they'll make it differently because they know it's so critical that when they come here, instead of having that round bar that we've talked about, they'll use big angles on each side that are welded in shear, as opposed to this little special type of weld. So they know that the highest loaded component is going to be very reliable. In this case, it was all the same. They were also using the cords to hang the tomato, and it wasn't really clear that this was taken into account in the design of the roof. So first day, just a quick inspection. You see that the tube for that lower cord, so this component, when you look at it on the side, it's just an empty tube for weight and cost reasons. And the shape of it, so the diagonal was welded right here, is unchanged. This has the same shape here where it broke than the other side. So visually, without going into too much detail, it's a lack of fusion. Now, there's another reason why you can tell that it's a lack of fusion is when you look at the upper part there, you can tell that it was coming at an angle with the surface. So when we talk about pore fusion, and we'll do it on a straight this time, so it's a little bit easier. So let's say I'm making a T connection. It's very, very common. And I'm going to come and weld. When my weld bead looks like this, just comes in at 90 degrees here, it's a little bit intuitive to think that you didn't heat up that much, that material, in this case this material as well, because of the your surface tension was very high there. When you heat up close to the melting point, this material, it's a liquid with a liquid, so it will spread, and let's say we'll do on the other side, we'll do a good one. The good one would look like this. So here you have a good contact angle, and it shows that both cases were fused, and now it was just a competition to extend an interface between the liquid and the fusion zone. So seeing that 90 degree on a weld is the first worry about not having enough fusion. Now, I don't want you to get too scared. So if you go to the gym and you see the equipment there, a lot of times what you're faced with is relatively thin material. So let's say there's a tube, any weightlifting stuff, and then you have this big bead that almost looks like it's not fused. Okay, so what happens here is if they melted and try to do something like that, they will perforate all the way through the base material. So they need to be limiting the fusion to something like this. And it could be that they don't have fusion everywhere, but it's so big of a weld as opposed to the thickness of the membrane goes all around the equipment that you don't have to worry about it typically. It's done this way, and the reason is by limiting that fusion, you don't have a burn through. So if you try to do this weld here, let's do it to the other side, it will burn through, and then things don't go well when you start doing that. So in automotive, that's one thing they do. They'll use processes that allow you to throw some metal and have limited fusion because you're all talking about sheet metal that's pretty thin. In this case here, it was a little bit intermediate. So the thickness of this member was, I think it was 1/8 of an inch, so about half the bead size. So they had to be a little careful, but they should have put more heat. So we went through that image before where you see it, that it didn't really fuse here, and it's almost perpendicular. So, and when you do weld inspection, I've done it a few times. I was a certified welding inspector, and the visual criteria is really to look for exactly how the bead is shaped to know if you have fusion or not. The AWS, and we'll go through standards a little later, just says it has to be determined by the inspector with the experience that he has, essentially. There's an ISO standard for weld inspection that is a little different. It essentially forces you to estimate that angle, and then you rate the quality of the weld based on that. So it's just a slightly different approach. So hope it doesn't surprise you. This is an actual weld. It doesn't look like the one I circulated. The one I circulated was a little smoother. So this is done with the stick electrode and the consumable, the shielded metal arc welding. So there was a slag on it, and what happens in this case is when you're done with the welding, you have to break down that slag. It's a little bit like a piece of glass that's dark and over the weld, and then you expose this. And on a process done by hand, a lot of times it's slower with that electrode, and that's why you see these striations of the welding. Now, this weld, a reason I photographed it, was one of the best that I've seen for this component because it had the fusion on both sides, and the roughness is really not a problem. So if you see a weld on the sport equipment that is very, very smooth, that itself is not a sign of quality. You really want to see how much it was fused, whether there's porosity in it, and things like that. But the striations are just the process of that pool growing step by step, just like when rocks solidify around volcanoes. It gives these cycles. It's very much the same. What happened with this project, the first thing was trying to repair in place, so qualifying welders, and it's just a process when you don't make the decision. So over there, I was there as a consultant, and essentially the company that made the greenhouse decided to honor the warranty. So they came in and said, we're going to fix the problem for you, very nice Dutch people, and don't worry about it. And it was kind of January. We knew there was going to be other snowstorm coming. They didn't want to shut down the whole operation. They had 30 people working in there. And they said, yeah, no problem, no problem. But they had 2,500 joists times 40 welds per joist. So things just start adding up, and you start calculating and say, well, it's going to be the summer, and we may be halfway through it. So it was very difficult to, I guess, deal with the issue other than shoring those joists. So they bought 2,000 posts, put them in the middle of each joist to take the load down by a factor of 2 or 3. And then this concept of having the welders over the tomato plant didn't get anybody excited. You have spattering and all sorts of things. So it turns out they all agreed to make new joists that we inspected, and they still weren't perfect, but they were definitely much better, and they actually added redundancy. So instead of having one diagonal, they had 2 diagonals in some situations. So we were okay with putting those in, but it was quite a process because they had a lot of drainage for the roof, electrical for heating attached to, and the crop attached to all these joists. So I can't emphasize enough that doing it right the first time is so great on a construction project, because when you have to do something like this, your costs multiply. It's not just a matter of remaking the joists, it's to putting them in place. Now, it is understood, and that's why a lot of times if you're building something big, you'll have construction insurance to make sure if something happens, you can do something about it. You have to exert good control over suppliers if you can. It's a very complex process, especially if you're doing something new. This was the first greenhouse like that up in Maine. But the Dutch, they don't really deal with snow day in, day out, so it was a little bit of a lesson learned for them. So why up in Maine? I think it's to supply us. They sell these tomatoes at least two of the local grocery stores, and they actually taste pretty good because it's all season long. It's almost fresh. You pick it up, and in 2 days into the Boston area. So it's a great technology to not have to import from Africa or California all the time and have the stuff shipped completely green. Now, these are not the only roofs. So if you go to Walmart, Costco, the airport, these structures are very, very common. We talked about it for the World Trade Center. So why do we have issues? There is a lot of redundancy. So when we're talking about a problem on a joist, except for a few exceptions that I remember, these are closely spaced, and there'll be one that breaks, it sags, and it's visible. And you have to come and say, okay, let's fix this one. Well, now maybe there's going to be ponding water on the roof, and it has consequences, but it's not the entire building collapsing. So the way the code is built for the fabrication of these joists does have provision for quality control of the wells and making sure it's inspected and it's tested, but it's not done as much as it would be for a pipeline, for example. And we can all decide whether that's acceptable or not. It's something that the buyers ultimately have to say, do I want the standard of care, or do I want something better? And if I do, then there's these third-party inspections. You can have special requirements. So you're going to meet the AWS code in addition to the Joist Institute code, for example. And that is done sometime. And other times when having a sag and a local repair is considered okay, then you have these things again. So this is a diagonal here on a tube, completely different project. It didn't fuse here. It only had a little bit of bite. You see the roughness in the corner here. That's all that was penetrating into the material, so it held for a couple of years, and then it broke after there was enough load or cyclic load. The top one is a little bit more complex, and I may have do I have an example of this? Maybe I do. But I guess you see from the images, so this is a different situation. You got two angles. It's a lot of kind of just geometry today, but maybe it gives you some idea on how you would build something efficiently. So you have an angle on one side, you have an angle on the other. These are very cheap to make. It's just by rolling. You don't need to do an extrusion, or you don't need to do a drawing to make an empty tube. So by weight, it's a lot cheaper to make these, and then you try to fit the diagonal in between. So let's say you put it there. Now, somebody very skilled has to come and weld that bar to the other components. So a lot of times they'll do it upside down. So they come from here, put a weld there, put a weld there. It's very quick, easy to do, but it's hard access, and again, a slightly different geometry on a flat against a curved surface. And that's what you see here. So the same situation where they welded a lot on the bar and didn't weld against the angle. So it broke. You can see the spacing, and then there's a repair weld because somebody got scared. And that was the first diagonal, this one here on the joist, that was bigger and supposed to be stronger. So this was a scoring facility, so the people that take the final exam from high school and things like that, and they have to process this. And of course, this started happening just before they had their peak season, and they needed to operate the facility. I mean, there's a reason why they were a certain size with these machine nerves to operate. So it was not a happy moment for the owner. This was a little different. So as far as rehabilitation, we felt comfortable fixing the ends here, especially knowing that the two local failures they had caused a sag of the roof as opposed to anything more than that. And they also had these big racks out there to store paper and whatever was going on. So it wouldn't necessarily fall all the way to the ground. But these are not easy decisions to make. I hope if you own something one day that's very valuable, you don't have to, after the fact, realize, oh, I had the option. You know, I could get this type of roof or I could get this type of roof because it's a lot harder to deal with it after the fact. And it is a topic that I cover more in the spring. When you go and say, I want this built, you know, you can specify the material, that's one thing. You can specify the process and the inspection, what kind of quality control you're looking for. And it's a lot of times not a huge added cost. So here we are talking about the code. These are excerpts from the code that give you basic information about things that naming stuff. So the root of the weld is kind of the far side, and sometimes it is a side of a pre-crack if your weld doesn't go through the corners. So the reason for that backup bar that we saw in the exemplar is to improve that root, so it is not a crack-like feature. The toe here is what we can see when we inspect and look for those angles here. So sign of having fusion, not too much fusion, those types of conditions. So it's very useful for that. And then there is a requirement. Oh, I didn't talk about this. Well, we did a little bit yesterday, that depending on the orientation of your weld with respect to the stress, it's going to have a different effect on how you need to reduce the load so you don't break. And that probably is intuitive. So if, in this case, I'm loading this way, it puts the root of the weld in tension, and that's a situation where my stress allowable, I'm sorry, this is in KSI, just the way it is. We talked about the strength of the steel, even the mildest steel, to be 30 KSI, and on the log scale here, the lowest strength steel weld, that is essentially a transverse weld, just like that, a fillet weld. So fillet weld here gives you this level of between 2 and 3 KSI, so 10 times less than the strength of the yield strength of the base material is what you can have for cyclic load. And I cannot emphasize, though, that if you're going to load it only once, you can go to much higher. It will typically be about 60, 70% of the yield strength of the base material. And what happens when you do that, though, is you'll have a little bit of a yielding of that surface that is in residual tension. So your dimensions can change a little bit. It's just part of that process. So there are ways where you get a better allowable. One of them is here, instead of having this fillet weld, let's say that I make a connection between two plates. One is tapered like this, and the other is straight. And I build up that weld. So that would be the case of a pipeline. And let's say I do it just from the outside. So I've got a number of passes. Well, over here, when you're all done, you have continuity. There's not really a little bit of a corner here. And the residual stresses in this situation, you get an actual deflection of the part because they're not connected otherwise. So you'll have a bigger allowable. And also, if you can weld from both sides here, that gives you an extra category here. So let's say we look at a category C. That is when you have all that reinforcement. So somewhere in here, above about 10 KSI. So we multiply by 3 just because we change from a fillet weld to a really good quality groove weld. It will have implication if you're building these little car or carts. There are people that are doing these competitions trying to build a small go-kart. They were somewhat lucky because it was already part of the competition, which material to use. So it's weldable and it's got a good combination of characteristics. So essentially, simplify the engineer's life by telling them what would be the highest strength they can use and a specific grade that can be welded without becoming brittle, all that martensite type discussion we had. And without having to reheat it, because especially on a big structure, if we take off a joist, trying to heat an entire joist so you relieve the residual stresses, it's a very tough job. It's not done very much. On large structures, so let's say you're building a power generation plant that's going to be used for a long time, and you have to use these thick materials. So a lot of times you will have a preheat procedure, and then you could also have a post-heat procedure after the welding to relieve the stresses, soften the microstructure, so temper the microstructure. The challenge in those conditions is to make sure that it's always done right all the time, because you really are talking about people bringing blow torches and getting the heat into the metal long enough and at the right temperature. So it's a very quality control intense process. When you don't do the heat treatment after the fact, this slide gives you some example, and there's a whole chapter on the ASM handbook here, volume 6, that shows you different patterns of residual stresses that you get in different direction. Maybe for us, this transverse stress here is one of the key components. So you can see on section C that in the center of the weld, you really have tension when you back down to the ambient temperature. And that's because your hottest metal was in the center, and then when it cooled, it went through more contraction than everything else. So it's left with that residual tension. One piece that is also important, this is the most important one from my standpoint, is tension, compression, the other part of the weld. But see, it goes back up. So in the heat affected zone, and that is the region just next to the fusion. So when we talk about heat affected zone, we're concerned about the material right here at the toe. That material went through essentially a heat treatment. It was heated up and cooled down fast. And a lot of times it will be in residual tension, and it's a place where the cracks can start. So I hope by my last lecture, when I emphasized why welding was great, that it was allowing you to do things fast, doesn't get overly diminished by this discussion. And let's go back to why we do it. So this is essentially monolithic, and you have it for motorcycle, for all-terrain vehicles, car, a little bit the same. If you take all the side panel, the side body off, you have a frame that has a lot of parts that are welded together using these templates or clamping that allows you to consistently get the same shape over and over again, and you can make big production. So this specific type of body, I've seen it done, and they will do, let's say this could be done in 5 sub-assemblies. So you have tables and you're working on a section of it, and at the very end they are all put together to make the overall assembly. Even though, let's say it's a motorcycle, you think like, oh, well, as long as the wheels are somewhat aligned. No, it has to be very, very precise. You have these cambers, you have all sorts of restriction that the dimensions are very critical for road stability. So what we discussed about, the issues of residual stresses are outweighed by these clamps, and these way to always do it the exact same way, and they'll have robots to go and do some of the welds, but they have to keep an eye on them. Every once in a while there will be variation. It's just the way welding is, especially these are empty tubes, so it's fairly lightweight. I would say that the the biggest consequence of a monolithic frame like that I have seen, and it does have some extra components. So here it is bolted for the arm, but let's say the frame here gets bent because you overloaded, you ran into something. A lot of times there's no real way to fix that damage because it's just an entire frame. So you have to replace the entire frame and remove everything else out of the unit if you damage the frame. And the main reason is there is no good way for you to get the right dimensional stability. So it's not as flexible. If you're going to build something and weld it all together when it's done, unless you don't mind that it's not as tolerant in terms of dimensions. So a lot of times, let's say there is corrosion somewhere or there's been a crack or damage, you can put essentially a patch over it. But if it's done in the field, then you have to worry, well, do I want to refinish the surface, and did I change the dimension of the assembly? And that's where it becomes a problem for vehicles, and it wouldn't be a problem for a building, for example. For a bridge, just like the Longfellow Bridge, which I worked on, you have to think about, if you're going to go and repair, you have to take all these considerations into account, because let's say you start in the old days with this very, very large, massive piece of steel. That's your 30 KSI type strength. And then you come and introduce all those stresses, go through a heat treatment, and you can start cracks. Now, so the idea of adding something to an existing structure is very, very challenging. Yeah, you need to know, let's say it's steel, so you need to know the chemistry. You have to do a test, figure out, can this steel be welded? And it happens, let's say, especially our MBTA system, the train system is very old. You go to a station, they have these beams. They're there, and yeah, it's steel, it looks rusty here, but you don't know if that steel was made to any specific specification as to where it can be welded. And a lot of times they're big sections. You have different floors involved, and the load, the design of the station may have changed over the past 70 years. And when you go and try to connect to an existing structure, you have to do these tests to make sure that you can qualify. So there's a very good reason for having those welding standards, I think you can see, because you can have so much variability. What the code says, and I'll go back to that slide. What this code tells you is if you have this type of steel, you can use this electrode, and it's going to give you these properties. It's very, very clear. If you don't know what kind of steel it is, you have to do enough testing to find an equivalent. And then you qualify your process that way. So it's a very, very good guideline, but when you go and ask for something to be welded, just like those arms, unless it's for making something that's very, very clear, it's calling for the welding code as the standard for quality and how it's been done, then people can build it other ways, especially if it's done overseas. So even though this material on how to qualify your procedure, qualify your welder, do the welding, and inspect the welding is all there, it needs to be called for a lot of times. Making a commercial building, for example, well, it's pretty clear because the building code just says, if you have structural component, they need to conform to AWS or the Steel Welding Institute. So it's for those other situations, and with aluminum, a lot of times it's the aluminum construction manual from the Aluminum Association that's used a lot. But again, you have to say, this is what you want. This is the electrode I'm looking for, and this is the kind of quality that I'm looking for. This code by default is only going to require a visual inspection. And that can be done by the contractor. So let's say you own a welding shop and you know what you're doing, you've qualified your welders, you can inspect their work and that will meet the base requirements. So anything that goes beyond that is a third-party inspection. Well, it has to be specified in the contract and organized so it happens and it's reported and it's got to be clear who is hiring it. If you require as a contractor to hire a third-party inspector and report on what he did, that's one thing, or maybe it's the owner or the buyer that's going to organize that. So they're just things set ahead, and the only reason, again, is there's a lot of variation. If making steel was that easy, maybe I wouldn't have a job. We talked about this a little bit last time about other ways you'll weld that don't involve the electrode type process. So we have friction welding, flash welding, where you put the arc on the two pieces and you ram them together. And resistance welding is just a small variation. Again, you clamp the two pieces together and you induce a current between them and you have a local spot fusion. They used a lot. I talk about it a lot, but I think it's just the idea there. A lot of times with the flash welding, we're talking about big components, and I think we'll do it for the last class. I have an example where for making huge chains that are based on this process here of just literally turning it on, fusing it, and what needs to happen is you move them together. And that's how you also, because we're talking about joining, if you take two pieces of plastic pipes to make gas distribution, a lot of times you'll heat them up and run them together so they deform together and they become a good fusion spot. So it looks like this one here, it has a reinforcement after the fact, and it's got pretty reasonable strength. It's not the greatest strength, but all those concepts of finding a way to have enough heat to either melt or soften enough are applicable both to metals and plastic. So I don't know if you have any questions. I'll stop the tape. Thank you.